Okay, so this is project test one. This is our fourth video, and it's problems 31 to 40. So a local real estate magazine used the median instead of the mean when it reported the SAT scores of the average students who attend Groveland High School. A graphical display of SAT scores of the students who attend Groveland indicated the data were strongly skewed to the right. So basically, they're telling us our data, it looks like this. That's not a very good skewed curve, maybe more like this, but it's been stretched out to the right. Which of the following explains why, in this situation, the median is more accurate indicator than the score of the mean? Basically, whenever we have skewed data, the mean will be pulled one direction or the other. So basically, if we said that the median happened to be here, the mean might be way up here. So the mean stretches it higher or lower than it should be. So when we have skewed data or outliers, we like to use the median. The median is not affected by skewed data because it's the middle 50%, whereas the mean is affected by skewed data and outliers. So the mean is affected by skewness, whereas the median is not. And that's something you're going to need to memorize. The mean is affected by skewed data. The mean is affected by outliers. The median is not affected by skewed data. The median is not affected by outliers. Also, standard deviation is affected by skewness and outliers, whereas IQR generally is not. Okay. All right. Number 32. The director of a fitness center wants to examine the effects of a 2-week exercise class, spinning and aerobics on body fat percentage. A 6-week spinning class and a 6-week aerobic class are offered at the same time and on the same day so that a person can enroll in either one of them. A new class of each is about to begin, and each class has 25 people in it. 10 people are randomly selected from each class. Each person's body fat percentage is measured at the beginning and again at the end of the class. Using the change in body fat percentage as the response variable and conducting a test at the 0.01 level, the director determines that there is a significant difference between treatment means. Which of the following is a confounding variable in the study? In other words, what is an outside variable that might impact the study? Okay, so in this particular case, people chose which class to take, and you're very likely to choose the class based on what type of athletic shape you are in, or your physical type. So that might impact a study. So the participant's choice of class is very, very likely to have a problem. All right. So that's likely to be the impact, is because people got to choose their treatment. Remember, we're always concerned that when someone chooses their treatment, there's a confounding variable implied in it. So number 33, Raul performed an experiment using 16 wind-up rubber band single propeller airplanes. He wound up the propeller a different number of times and recorded the amount of time in seconds that the plane flew for each number of rotations the propeller was wound. A regression analysis was performed and the partial computer output is given below. Which of the following is a 95% confidence interval for the slope of the regression line? So whenever we're working with regression, we need to make sure we identify all the parts. So when we're looking at the actual slope, basically we're going to be needing our coefficient. We're going to need our confidence interval, our confidence level, and we're going to also need the standard error. So basically it's going to be B plus or minus our T star times our standard error. Now we have to be really, really careful about this. All right. So one of the things that we have to be really careful about is we need to make sure that we know that our degrees of freedom. For a regression test, degrees of freedom equals n minus 2. So in this case, 16 minus 2, so it's 14. All right. And our slope is going to be 0.04625. This very first value here, plus or minus. We'll have to come back to T star, but they give us our standard error, which is always really nice because we can get it straight off of this. It's already been divided by the sample size. And that becomes 0.01565. So this is something that comes right off the table. So that's really nice. But one of the things we're going to have to go calculate is our T star. So second vars, inverse T. And they want to construct a 95%. So parenthesis 1 minus 0.95, close parenthesis, divided by 2. And our degrees of freedom are 16 minus 2, or you could just type 14 in. When we do that, we end up getting 2.144, or 2.145 is probably pretty close. And we can see real quickly that our best answer is letter A. So letter A would be our best answer to 33. Once again, slope, standard error, and then we had to calculate our T star, being sure to use degrees of freedom for the regression, 16 minus 2, because it's n minus 2 for regression. All right. A recent study, this is number 34, was conducted to investigate the duration of time required to complete a certain manual dexterity task. The mean was reported as 10.2 with a standard deviation of 16. Suppose the reported values are the true mean and standard deviation for the population. So they're telling me that these are not sample values. These are the actual values. So the mean is 10.2. And the standard deviation of the population is 16. Now, since this is standard deviation of the population as opposed to standard deviation of the sample, I can use a z-test, all right? And there's a couple different ways to look at this, but this is basically telling me the standard deviation they gave me standard deviation of the population, so I get to use a z. Standard deviation of the sample, then I use a t, but standard deviation of the pop, I use a z. Suppose if a random sample of 144 subjects is selected, so n equals 144, what is the approximate probability that the mean of the sample will be more than 110? So the mean of the sample now. So here's what we have. We have this graph. We have an actual mean of 10.2, and they want to know, then that's the population mean. They want to know the likelihood that I get an X bar that is 11 or larger. So they want to know the probability that X bar is greater than 11, which is equal to the probability that Z is greater than 11 minus 10.2 over, my standard deviation was 16, but they gave me a sample size of 144. Now there's a couple of ways to do this, but I'm going to go ahead and run a z-test because that's going to be probably the fastest. So stat test, z-test, mean of 10.2, standard deviation of 16, X bar is 11, my sample size is 144, and we're looking for the probability of it being greater than, so I need to make sure I have that highlighted. And I end up getting a p-value of about 0.27. So there's a 27% chance, or this area right here is 0.27. There's about a 27% chance I would get a sample of 11 or greater if the population average was really 10.2 and the standard deviation was 16. There's a 27% chance by random chance alone that I would get a statistic that looked like this. All right, number 35. To determine whether employees at site X have higher salaries than site Y, 2 independent random samples were obtained. So we have two independent samples. So it's going to be a 2 of something test. Based on the sample, what are we doing? So now we have sample mean. So this tells me, hey, we have sample means. This is standard deviation of the samples. So these are S's. So this is going to be a 2-sample t-test. 2-sample t-test for means, because we're working with means and we're working with a standard deviation of the sample. All right, so I'm kind of short on space here, but it's going to look something like this. X bar 1 minus X bar 2 over something like that. Now I can plug this directly into the calculator, and that's what I'm going to do. And they want to know whether site X have higher salaries than site Y. And it's going to be really important because we're going to be going X is greater than Y when we do this. So here we go. We're going to go stat test, and we're just going to screen through the calculator really fast. Stat test, 2-sample t-test. X1, our mean was 61,234. Our sample standard deviation was 4,352. Our sample size is 235. For the next group, 60,529. A standard deviation 3,456. Sample size 183. We said greater than, so we need to make sure that it's highlighted on a greater than. Remember, we never pool unless it's proportions. And I end up getting a p-value of 0.03. Well, this tells me it's significant at alpha equal 0.05. So I'll be rejecting at alpha equals 0.05. So at the 5% levels, site Y have significant, no, not site Y, it's site X have higher. That's wrong. At the 1% level, employees at site Y, it's not even significant at the 1% because we had a p-value of 0.03. So 0.03, if our alpha is 0.05, this is less than, that's going to be significant. But if it was 0.03 compared to 0.01, it's not significant. So not significant at the 0.01, significant at 0.05. At the 5% level, site X have a significantly higher mean salary than those at site Y. This is true. We know that's true because it's significant at that. At the 1%, have a significantly higher than site Y. No, it's not significant at the 1%. It was significant at the 0.05%. All right. Number 36. The director of a technical school was curious about whether there is a relationship between students who complete one of the school's most popular health science certificate programs and whether those students go on to complete more advanced studies in healthcare students within 2 years of completing the certificate program. She randomly selected 100 students who completed the program. Data collected on these students are shown in the table below. All right. Which of the following statements are true for these 100 students? Being a person who completed more advanced studies is more likely than those who did not. So let's look at this. More advanced studies is 40 over 100 versus 60 over 100. Well, more advanced is not more likely. The person who completed the program is less likely than a person who did not complete the program. So let's look at completed the program. Completed the program. Well, we have 60 over 100, which is greater than the 40, and they said less likely, so that's false. Being a person who completed the program and completed more advanced study, person who completed the program and completed more advanced studies. So that's going to be 35 out of 100. Is less likely than being a person who did not complete the program. So did not complete the program means we're looking here. And did not complete advanced studies. Well, they both happen to be 35 over 100, so they're not less likely, they're equal. Both are equal to 35 over 100. Being a person who did not complete the program but completed more advanced studies. So did not complete the program but completed more advanced studies is 5 out of 100. 5 out of 100 did that. And is less likely than being a person who completed the program and completed more advanced studies. And that one is 35 out of 100. So obviously this is less, this is true, that's correct. Now, some of you may be asking, why didn't I divide by the marginals? And I'll be honest with you, they did a really poor job with this question. Fortunately, if you had divided by the marginals, you'd gotten the same answer. But since they weren't very specific, I used the total. But it was not the best worded problem. So I can understand why there might be a little confusion on that. Number 37. On their birthdays, employees at a large company are permitted to take a 60-minute lunch break instead of the usual 30 minutes. Data were obtained from 10 randomly selected. We have a sample size 10 on the amount of time that each took for their lunch on his or her birthday. The company wishes to investigate whether these data provide convincing evidence that the mean time is greater than 60 minutes. Which of the following would not be expected to be part of the process? So we're looking for not in conducting a hypothesis. Being willing to assume the distribution of actual birthdays for all employees is approximately normal. You have to assume they're normal. It's a small sample size. It's not normal by central limit theorem. So we're going to have to assume that it's normal or graph it out or something. Something on the lines is going to tell me I got to have to assume this. B, knowing that there are no outliers. And by the way, if you don't like the word assume, you can put a question mark and go, is there a better answer? And honestly, this might be one of those choices where he's like, hey, I need to see if there's a better answer out there. Knowing that there are no outliers in the data. Yes, you have to know that there are no outliers in the data because we're working with a small sample size. Using a t-statistic to carry out the test. Well, we're taking it from the sample, so we're definitely using a t-statistic. Using 9 for the degrees of freedom. Well, the degrees of freedom is going to be n minus 1. So in this case, 10 minus 1, so 9. So this is also true. Given the p-value is greater than 0.05, reject and annul. Oh, wait a second. When do we reject? We reject if the p-value is less than alpha. So I would not expect this. This is false. Therefore, that is my best answer. All right, we don't reject when it's less than 0.05. We fail to reject. 39. A statistics student wants to compare the mean times needed to access flight information for 2 major airlines. 20 randomly selected students access one airline's website, and the time required to locate the flight information using the website had a mean of 2.5 and a standard deviation of 0.8. 20 different randomly selected students access the website and time to locate the flights, and that had a mean of 2.1 and a standard deviation of 1.1. Now we have 2 independent samples of 20. This is important. So since we have 2 independent samples, we have 2 means, we're running a 2 sample t. This will be a 2 sample t for means. So let's go ahead and run this because they want to know, assuming the conditions for inference were met, which of the following statements about the p-value obtained is true? Well, obviously we didn't calculate the p-value yet, so we're going to have to do that. So what do we get? Stat test, 2 sample t-test. We have a 2 sample t-test, and our first one has a sample of 2.5, and I guess I should have used the X bar. That would have been more correct. X bar of 2.5, a standard deviation of 0.8, sample size 20. Next one had a mean of 2.1, a standard deviation of 1.1, and a sample size 20. And they didn't give a direction. Because they didn't give a direction, I'm going to have to use a not equal. They didn't tell me one's greater than the other. And this always bothers me when this happens, but I get a fairly large p-value, all right? And so in this case, I get a p-value of 0.197. Well, with that type of p-value, that's larger than any alpha. So because it's larger than any alpha, I'm going to fail to reject, all right? Because it's larger than any reasonable alpha, I'm going to fail to reject, which means there's not a significant difference. By the way, I skipped number 38. Sorry about that. So we went out of order here. Number 38, a dog food company wishes to test a new high protein formula for puppy food to determine whether it promotes faster weight gain than the existing formula for the puppy food. Puppies participating in an experiment will be weighed at weaning when they begin to eat puppy food, and will be weighed 1 month in intervals for each year. In designing this experiment, the investigators wish to reduce variability due to natural differences in puppy growth rates. Which of the following strategies is most appropriate? Okay, so when I look at this, I see block and I see stratify. That's really important here. We block for experiments. We stratify for samples and surveys. All right, we stratify for surveys or observational studies, but we block for experiments. So stratify can't be it, because this is an experiment. We're assigning them. We're randomly. And I know it's an experiment because I'm making a random assignment. So what are we going to block on? Well, we're going to block on what we think impacts things. And while geographic location may have some sort of impact, bigger dogs may live up north or smaller dogs may live up north. Really doesn't make a whole lot of sense. But dog breed does impact how fast puppies grow. So breed of dog impacts it. Obviously, if you have a Great Dane, it's probably going to grow faster than a Maltese. So block on dog breed as we think it'll have the largest impact. All right. So you're going to block on dog breed. Okay, number 40. I'm just going to tell you real quickly that I think this is not that great of a problem. In fact, my first year teaching AP Stats, when I went to an AP Stats training, I said, how do you teach this problem? And this is to the College Board presenter. And he said, I don't know, it's a bad problem. Without statistical data or statistical packages, is very, very difficult to show. Since then, I've kind of come up with my own way of presenting it, but really the only reason I knew this is because I'd worked with statistical packages. Otherwise, I wouldn't have known this. But so I wouldn't expect you to know this, but I think this is going to make sense. Let's just say we have two choices. Let's say our two choices are 0 and 1. And you're like, well, why? How are you saying this? Well, it's not exactly true, but I almost have a goalpost. I almost have, it can happen. You can either get a 0 point or you can get 1 point, and you really can't get anything in between. So basically, you either get 0 points or you get 1 point. And I know it's really not 0 and 1, but we're going to make it for simplicity's sake. We're going to say that that's your only two choices. So you play a game once, you can either get 0 points or 1 point. Well, we're taking samples of size 2. And by the way, if this had been sample of size 30 or more, this would be easy. Normal by central limit theorem, it's E. But we have samples by size 2, so we're not approximating the normal. So it's like, darn it, I'm not approximating the normal. what is this going to look like? I have sample size 2. Well, I've generally said that when you have a sample of size 2, probably best off making some sort of sample space. So in this case, I'm gonna say, you know what? If I have a sample size 2, I could get a 0 on the first game and a 1 on the second, excuse me, a 0 on the first game and a 0 on the second game. I could get a 0 on the first game and then get a 1 on the second game. Or I could get a 1 on the first game followed by a 0 on the second game. Or I can get a 1 on the first game and a 1 on the second game. And those are really my only combinations. I can get 0, 0, 0, 1, 1, 0, and 1, 1. Like, I'm not sure how this is helping me yet, Mr. Spencer. Well, what's the average of this? The average of that is 0. How often did that happen? 1/4 of the time. All right. Here, what's my average? My average of this is 0.5. And how often did it happen? Well, it happened 2 out of 4 times, or 50%. And here, my average, 1 plus 1, is 1 whole. And that happened 1 out of 4 times, or 25% of the time. So it's like, oh, 0 is 25%, this is 50%, this is 25%. Well, which one looks like that? Well, high in the center, maybe about 50%, low at 0 at 25%, and here at 25%. This is my best answer, but I'm going to just tell you real quickly, very challenging problem and not the best one ever. But once again, if you're doing something twice, it really helps to make a sample space and a table. All right, thank you.